this computer. Okay, so we're here. It's August 31st, Monday, and we're here to talk to our introductory chemistry class, and we're going to talk about ion formation today. So I mentioned that an ion is an electrically charged atom or group of atoms, so we can write that down. An electrically charged atom or group of atoms. Okay, now we know that the two types of electrically charged particles that make up atoms are protons and electrons. Okay, and we cannot make an atom positive by adding protons. We cannot make an atom negative by taking away protons. For the simple fact that protons are tied up in the nucleus. Okay, during a chemical reaction, we cannot get at those. Okay, so that leaves the only other viable option is to alter the number of electrons. If I have a neutral atom and I take electrons away, then I have more protons than I do electrons, and the atom will be positive. If I have a neutral atom and I add excess electrons to it, I'm adding negative charge, the atom will go from neutral to negative. Okay, so we're going to take a look. I'm going to take over the screen here, and I'm going to put up, and I had emailed this earlier today. And I don't know if any of you got a chance to print it out. Let's blow this up a little bit. I guess I can't. Okay, there we go. So what we have here, now we're going to take a look on the top here, the top row first. And what we have is a consecutive run by atomic number off of the periodic table, starting here at carbon, all right, atomic number 6, 7, 8, 9, 10, on up through 13, aluminum. All right, now notice that this is somewhat centered about the inert gas. Okay, neon's the inert gas. Okay, to the left of the inert gas, I have the nonmetals, carbon, nitrogen, oxygen, and fluorine. To the right of the inert gas, I have the metals, sodium, magnesium, and aluminum. Okay, so we have a consecutive run off of the periodic table. All right, all these atoms are neutral. All right, all these atoms are neutral. For each atom, the number of protons equals the number of electrons. Now I've written the electron configurations up here also. All right, notice that the charge in each case is 0. Consecutive run on the periodic table. Okay? All right, so that's pretty straightforward. What do we have on the bottom here? I've taken those same atoms, same consecutive run off the periodic table, and now I have altered the number of electrons. I have altered the number of electrons. All right, so if I take a look here, all right, now the neon, the inert gas, is still neutral. It still has 10 protons and 10 electrons. And now if I look at fluorine next to it, I've added 1 electron. So 9 positive protons and 10 negative electrons gives me a charge of -1. All right, a charge of -1. All right, here oxygen, right next to it, I have 8 protons and 10 electrons. So I have 2 excess negative charges for a total charge of -2. Right, and so forth for the nitrogen and the carbon. Okay, now, so the nonmetals all have negative charges. I have added electrons to them. I have added electrons. Notice that they all have 10 electrons now, the same as the inert gas that they're near. All right, any questions there? All right, so I've added electrons to the nonmetals. They all have negative charges now. All right, now let's go on the other side. On the other side, we have the metals. To the metals, I took away electrons. Sodium started with 11 electrons, now it only has 10. Right? Well, if I have 11 positive protons and 10 negative electrons, that's 1 excess proton, so the charge is +1. Right? The charge is +1. Similar to magnesium, right next to it, the alkaline earth. Okay? So I started with 12 protons and 12 electrons up here. Now I'm down to 10 electrons. That means I have 2 extra protons. So the charge on the atom goes from neutral up here on the top row to +2 down here. 2 excess protons is a net charge of +2. And similarly with aluminum. right? Aluminum, 13 positive protons, 10 negative electrons, gives me a net charge of +3. Notice that in each case here, in the bottom row, all the atoms have 10 electrons. All the atoms have 10 electrons. So there must be something special about this number 10 that we'll get to in a few minutes here, right? There must be something special about this number 10. Notice that the number 10 is equal to the number of electrons in the neutral inert gas element, 10, the neutral inert gas element. Now, these trailing superscripts here in the bottom row, right? The trailing superscripts are the electrical charges. For example, carbon has a net charge of -4, and I've written it as a superscript here, right? Over here, so magnesium has a net charge of +2. I've written it as a trailing superscript. Okay, now notice that since they all have 10 electrons in the bottom row, they all have identical electron configurations, which is the same as the neutral inert gas element. The same as the neutral inert gas element. Right, so there's something special about this number 10 electrons, and there's something special about the inert gas. I kind of have it written on the bottom there, but we'll get to that in a moment. Okay? Now, I want to point out here, we're focusing on the bottom row here. All right? Centered about, think of this back when you were a student, second grade, third grade. And the teacher probably had a number line across the top of the room, the front of the room, across the top. So everybody could see the number line. And in the center, we had 0, right? That's our inert gas. So our numbers on the number line are going to be the electrical charges here, right? Now again, this is a consecutive run of elements on the periodic table, 6 through 13, going by atomic numbers, right? But now we're going to focus on the electrical charges, right? They're going to be our numbers on the number line. So the inert gas is our 0. Then I have a metal, +1, a metal, +2, and a metal, +3. So the metals lie to the right of 0, to the right of the inert gas, the higher atomic numbers. And they have positive charges, +1, +2, +3. On the other side of the inert gas, we have the nonmetals. And in this case, all right, we see the first nonmetal that's 1 away from the inert gas has a charge of -1. 2 elements away from the inert gas has a charge of -2 and 3 and -3 and -4. So so notice here, these are just like numbers on a number line. All right, the inert gas is 0, the nonmetals are -1, -2, -3, -4. All right, go back to the inert gas has a charge of 0, and the metals are +1, +2, +3. All right, so this is going to be the case regardless of what inert gas we're centered about here. The metals will always be +1, +2, and the nonmetals will be -1, -2, -3, maybe -4. Okay, depending on what period we're in. Okay, so we could use this to predict the charges. So over here, I have positively charged metal atoms. Positively charged metal atoms. To the left, I have negatively charged nonmetal atoms. Negatively charged nonmetal atoms. Okay, now I'm going to stop sharing the screen here. And I'm going to write 2 more words up here. All right, now we had said a moment ago that an ion is an electrically charged atom or group of atoms. So how about, so if I say, oh, there's a charged atom sitting on the table there, okay? And I don't know if it's a positive metal or a negative nonmetal. So how can I can be a little more specific than just saying, oh, there's an ion sitting on the table. If I say there's a cation sitting on the table, a cation, okay, this is a positively charged atom or group of atoms. A positively charged atom or group of atoms. So that would be our metals, sodium +1, magnesium +2, aluminum +3. And again, as always, if you have a question or comment, do not hesitate to stop me. All right, nobody ever does. All right, so a cation is those positively charged metals. Now, for today, we're just going to talk about monatomic ions. In other words, ions made of just one atom. And remember, a cation can be a positively charged atom or group of atoms. Today, we're just going to talk about atoms. Okay? Now, so if a cation is a positively charged atom, then we must have some sort of name for negatively charged atoms or groups of atoms. And we do. Negatively charged atoms are called anions. 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 All right? So here are the positive metals and the negative nonmetals. Right? So this would be our sodium +1, magnesium +2, aluminum +3. Down here would be our fluorine -1, oxygen -2, nitrogen -3, and carbon -4. All right, carbon -4. All right, now, does anybody see an easy way to remember which one is positive and which one is negative? Whether a cation is positive or negative, or is it the anion that's positive or negative? Anybody see an easy way to remember that? I noticed this a few years back. I don't know if this is how it got its name, but if we take a look here, the negative ion, a negative ion, right? I don't know if that's where the name came from, but it works. It works. So these, anytime you have access to one of these little learning tools, by all means use it. A negative ion. Then by default, the cation is going to be the other one. Okay? So no one should ever screw this up, saying that anions are positive and cations are negative. If you remember this, you should never screw it up. Never screw it up. Okay, any questions or comments so far? Now, if I'm going to take over the screen again here. So what's so special about this number 10? Let's see, share screen. And we have this little rule on the bottom here. It's one of the major driving forces behind all of chemistry, right? It's called the Octet Rule. The Octet Rule. All representative atoms want to be isoelectronic with the nearest inert gas. Now, we haven't said what this word isoelectronic means, but from our last class, we should know. What does that prefix iso mean that we learned last class? What's the prefix iso mean in Greek?
Same.
Same. So isoelectronic is same electron configurations or same number of electrons, right? Whichever way you want to look at it, right? Because at least for our purposes right now, the same electron configuration implies same number of electrons and vice versa. Okay, for our purposes right now. Right now, let's dissect this octet rule. It's very, very important. You need to get that written down and put a box around it with stars all around it. It is extremely important. Again, I'm not going to say most, a lot of chemical reactions occur because of this octet rule. All right, so let's dissect it. First off, all representative. So representative, we're only talking about S&P block. We're only talking about S&P block. Want to be isoelectronic. In other words, same number of electrons. Same number of electrons. Okay, so atoms in S&P block want to have the same number of electrons as the nearest inert gas. You guys can see my cursor there, right? Hello?
Yes. Yeah, I can see it.
Okay, so all atoms in S&P block want to have the same number of electrons as the nearest inert gas element. As the nearest inert gas element. Notice this does not apply to D and F block, the transition elements. Okay, so this is what's so special about these 10 electrons. These 10 electrons, which the inert gas in this case has. The nearest inert gas is neon, which has 10 electrons. Okay, so what's so special about the inert gases? What's so special? Well, we saw that from the very first day that by and large, they don't participate in chemical reactions, at least in nature, right? We can force them to in the laboratory, but in nature, they're always by themselves. So there must be something special about them. Well, they're at lowest energy. Most things in nature want to tend to be at lowest energy. That's why all you guys are sitting down and I'm standing up. Right? It's lower energy to be sitting down. I mean, we prefer to be at lowest energy. Right? So the inert gas elements are the lowest energy atoms on the periodic table, all right, as a group. Okay? So atoms want to get, most systems want to strive to get to lowest energy. And so these representative atoms can do that. If they're metal atoms, they can get to lower energy by losing their valence electrons. If they're non-metal atoms, they can do it by gaining valence electrons. Okay, and so why is it called the octet rule? Anybody have any idea? Why the octet rule?
Because there's 8 elements total in each group.
8 elements?
Well, there's the carbon, nitrogen, oxygen.
There's 8 valence, well, there's 8 valence electrons, right? There's 8 valence electrons in the inner gases, except for helium, which only has 2. Except for helium, which only has 2, right? 8 valence electrons. Neon has 8 valence electrons, argon has 8, xenon has 8, krypton has 8, radon has 8, right? 8 valence electrons. Although I prefer to look at it this way, since helium is an exception to that rule, and I'm gonna put a different thing up. I'm gonna take over the screen again, but put something different up. Okay, so here we are with the SP, D, and F blocks. All right, and let's see here. Let's blow this up a little bit. All right, if you look here, we're in Roman numeral group 8. Roman numeral group 8. So I like to think of it in those terms, right? Then you don't have to worry about helium being an exception. Although most people will think of it as there's a full octet of valence electrons in the inert gases, except for helium. Another way to think about it is they have what are called closed shells. So that would include helium. So 1s2, that's a closed shell. All right. Neon has a closed shell, 2s2, 2p6. All right. But I don't want to dwell on that too much. But again, you should understand all these representative atoms want to be isoelectronic with whatever nearest inert gas is closest to them. Now, while I have this periodic table up here, right, we're going to spend a good bit of time here on this, because you have to be able to look at the periodic table and predict the charges of these representative atoms. And it's very, very, very simple to do. Very simple to do. All right? Let's go down here to argon. All right, so here we're at argon. All right? And, well, I know, so argon has a charge of 0. Now let's go to the left, to the nonmetals. Chlorine will be -1, sulfur will be -2, phosphorus -3, silicon -4. All you have to do is ask yourself, am I dealing with a metal or a nonmetal? Well, I'm dealing with nonmetals. I know nonmetals form negative ions. They form anions. So that gives me the positive or the negative. And then to get the number, it's just how far away is it on the periodic table from that nearest inert gas? -1, -2, -3, -4. Just like a number line. Let's go back to argon again and go towards the metal side. All right, so I'm at argon, which is 0. And here is potassium +1, calcium +2. All right, now it doesn't apply to D block, so we can skip over that. I could go to gallium, and gallium is +3. Gallium is +3. Okay? Gallium is +3. Again, they lose their valence electrons. Now, gallium will not strictly be isoelectronic with argon, because when gallium loses the 4s2 and the 4p1, it still has the 3d10, which argon does not. Right? It's still, but its charge is +3. Its charge is +3. Let's go to krypton here. Let's go to krypton. Now we're going to do a little bit of oral drilling here in a few minutes, so you better be paying attention. Okay, so krypton is 0. It's the inert gas. All right, I'm going to go to bromine. And I ask myself, is bromine a metal or a non-metal? Well, it's a non-metal, so I know it's going to be negative. All right, negative how many? Well, it's 1 away from krypton, so -1, selenium -2, arsenic -3. All right, arsenic -3. All right, let's go on the other side of krypton, towards the metals. All right, krypton is 0, rubidium is +1, strontium is +2. I could even jump across and say indium is +3. All right, indium is +3. Okay, I could go down to xenon, number 54, neutral. Iodine's -1, tellurium -2, antimony -3. I don't go to tin because tin's a metal. All right, now I go to the other side, on the plus side of xenon, which are the metals. Metals form positive cations. So if xenon is 0, then cesium had better be +1 and barium had better be +2, which they are. Which they are. Okay? Any questions or comments there? Any questions or comments? I'm going to stop sharing here. Nobody, everybody's expert on ions, predicting ion charges. Right? Predicting ion charges. Nobody has any questions or comments?
No, at the moment.
Sorry? All right, I'm going to take over the screen again. And before we do the oral drilling, I'll just do a few more. All right, just so until you guys feel a little more comfortable with this. All right. Wait a second. Zoom. There we go. All right, I should have just kept this up there. It's wasted time. All right, so suppose I want to know the charge on a calcium ion. A calcium ion. First question is I ask myself, right? And if you have a periodic table in front of you, I would strongly advise that you put your finger on the periodic table and count. Don't think, oh, you know, I'm an adult, I don't have to do that. All right, because you'll never make a mistake if you put your finger on the element and count. So the first thing I'm going to do, I'm going to ask myself, is calcium a metal or a non-metal? Well, it's a metal. So I know it's positive cation, positive. Positive how many? I'm just going to count to the nearest inert gas. +1 at potassium, and then +2 to argon. So calcium's charge is +2. It will have an identical electron configuration with a neutral argon atom. It will have identical electron configuration with a neutral argon atom. Let's look at arsenic. All right, arsenic. Well, the first question I'm going to ask, is it a metal or a non-metal? Well, it's neither. It's actually a metalloid. But for these purposes, for this purpose, for ion formation, we will consider metalloids to be non-metals. Right? They are literally not metals. All right, so I'm going to say negative. Negative. Again, the metalloids we consider to be non-metals. So arsenic will be negative. Negative how many? -1, -2, -3. It's 3 away from krypton, so its charge is -3. Its charge is -3. Okay, let's take a look at tellurium, number 52 here. All right, first question I'm going to ask myself, is it a metal or a non-metal? Well, tellurium's a metalloid, so negative. All right, metalloids are negative. All right, negative how many? Count how far away from the nearest inert gas. Iodine -1, xenon -2. So tellurium's charge will be -2. -2. Okay? Now, let's go over here to magnesium, or let's go to sodium. Sodium, number 11. Actually, that's one you have on your sheet. Let's go to beryllium. Beryllium. First question I asked, metal or non-metal? Well, beryllium's a metal, so I know it's positive. Positive how many? Count to the nearest inert gas. 1 to lithium and 2 to helium. So beryllium will be a cation with a charge of +2. Cation with a charge of +2. Okay? Now, let's take a look at, now pay attention to helium here. I'm going to go over helium here. Right, so helium has a charge of 0. Right, the metals, lithium +1, beryllium +2, as we just saw a moment ago. Now I go to the opposite side of helium. I go to the non-metal, which is hydrogen. Hydrogen is -1. Hydrogen is -1. All right, hydrogen is -1. All right, but I want to focus on hydrogen here for a moment, so I'm going to stop sharing here. All right, now I just said hydrogen is a non-metal, so it's going to be a negative anion, which is okay, it's true. But hydrogen is unique amongst those representative elements. For hydrogen can also be a positively charged cation. Let's take a look in greater detail at this. All right, in greater detail. So I can have a neutral hydrogen atom. All right, a neutral hydrogen atom. All right, so number of protons and the charge. This means 1 proton and 1 electron. All right, do we all agree on that? All right, now let's look at hydrogen anion. So still has 1 proton because it's hydrogen, and now it has a charge of -1. We always, for some reason, we always put the number first and then the sign on electrical charges. Okay, I had all my assignments the other way, and one summer I spent a day reversing all the charges. All right, well, it still has 1 proton because it wouldn't be hydrogen if it didn't have 1 proton. How many electrons are here? How many electrons?
1 proton, 1 electron.
You gotta
2.
speak louder.
There's 2 electrons.
2 electrons. Right, 2 electrons. Now, let's look at a hydrogen cation. 1 H, 1 plus. Well, it still has 1 proton. How many electrons?
Would it be
3.
Not 3.
1.
So that 1
0.
would be neutral.
0?
0. 0 electrons. Zero electrons. Okay? So in other words, a hydrogen cation is just a proton. It's just a proton. It is the smallest of all possible atoms. All it is a proton. It's nothing else. Just a proton. All right, so I don't know if you're into astronomy at all, but you may hear that, oh, hydrogen is the most dominant element in the universe. I can't remember what percent of the universe is made out of hydrogen. It's something like 90% or 70%, 76% or something, right? But really what they're saying, it's not that we have this floating around. What we have floating around is a lot of protons, a lot of protons. That's the same in the sun. How does the sun generate light and energy? Well, the sun is turning hydrogen into helium, as they say, be it a proton-proton cycle, all right? And does that mean it's turning this into helium? No, it's combining, it's fusing two protons into a helium nucleus, right? Actually, 4 protons get turned into 2 protons and 2 neutrons. But again, there aren't any electrons, right? The temperature is way too high for electrons to be bound to the nuclei. So it's just turning protons. But we say that because a single proton is the same as a hydrogen cation, we say the sun is fusing hydrogen nuclei into helium, right? Which is true, right? But remember that hydrogen cation is nothing more than a single proton. Nothing more than a single proton. Okay, any questions there? Again, hydrogen is the only one that does this. Okay, common. Okay? All right, let me put that periodic table back up for a moment. All right. And we'll zoom in again. Okay, already is zoomed in. All right, I'm going to call on a few folks here, okay? I'm going to call on a few folks. And again, when I call on you, the first thing you should do is find the element, put your finger on it, and then ask yourself, is it a metal or a non-metal? Remember, metalloids count as non-metals in this case. Is it a metal or a non-metal? If it's a metal, you know it's positive. If it's a non-metal, you know it's negative. And then just count to the nearest inert gas. Just count to the nearest inert gas. Okay? So let's see here. Mr. Lucas. You there, Mr. Lucas? Lucas. Hello, Lucas. Did you check out?
Oh, sorry.
Are you there?
Yeah, I'm here.
All right. Lucas, put your finger on strontium, number 38, in S block.
All right.
You got it?
Yes,
What's the charge on the strontium ion?
+2.
Louder?
+2.
+2 is correct. Very good. Let's see. Miss Aaliyah, put your finger on number 34 in P block. You got it?
Yeah.
Okay. What's the charge on selenium? Is it a metal or a non-metal?
I'm not too sure.
You don't remember where we drew that line from? Hello, Aaliyah, come on, turn your microphone on. Your speaker on. Microphone.
Yeah, sorry, I'm kind of confused.
Leave your microphone on. Come on, you're on. Why you keep turning it off?
Sorry, I'm kind of confused.
Well, I'm going to help you. All right, so you have your finger on selenium.
Yeah.
You remember where we drew the line to separate the metals from the non-metals?
No.
We drew it from boron down here to polonium. So selenium to the right or to the left of that line?
To the right.
To the right. So does that make it a metal or a non-metal?
Metal?
No, it's a non-metal.
Okay.
So if it's a non-metal, does that make it positive or negative?
Positive.
Makes it negative. Negative how many? Count to the nearest inert gas.
-2.
-2. -2. So it's isoelectronic with which inert gas? What inert gas did your finger end up on?
Gallium.
Do you know which elements are the inert gases? What group number is the inert gases, Aaliyah? What group number? 1 through 18. Which one is the inert gases?
13.
It's 18. Come on, you should know that by now. It's 18. I mean, you should, even if you had forgotten it before class, you saw me going through all these examples. You should realize these are the inert gases. These are the inert gases. Okay, let's see. Michael, you up? You're up. Michael, put your finger on number 53, iodine. You got it? Michael, I'm talking to you. Michael. Earth to Michael. So he's not there.
He doesn't have audio, he said. He's on chat.
What happened to my chat window? I don't even see my chat window. All right, Marissa then. You there, Marissa?
Yes.
All right, Marissa, iodine, number 53. You got it?
Yes.
Is it a
Negative
metal
one,
or non-metal?
non-metal.
Non-metal, so positive or negative?
Negative one.
-1. So it's isoelectronic with which inert gas?
Xenon.
Xenon is correct. Xenon is correct. Let's see, let's do a couple more here. Angela, put your finger on number 56. Over in
Got
S
it.
block. You got it?
Yes, sir.
Barium. Is that a metal or a non-metal?
Metal.
Metal. So positive cation or negative anion?
Positive.
Positive. Positive how many?
Positive 2.
Positive 2. So it's isoelectronic with which inert gas?
Radon.
Look at the atomic numbers and go backwards to the nearest inert gas. Which one is it
Oh.
isoelectronic with? Louder?
It's not radon?
Take a look here. Barium is 56, right?
Right?
You're counting to the nearest inert gas. Cesium is 55. How do you go from 56 to 55 to 86?
Oh. Sorry, xenon.
Xenon, right.
Xenon.
Got it? So when I say count to the nearest inert gas, we should be looking at atomic numbers. We should be looking at
Got it.
atomic numbers. Now, I just want to point out here, before I said gallium is +3. All right? Please pay attention to gallium and indium, because gallium is a metal, so it's positive. And some students want to say positive, well, go to the nearest inert gas. +1, +2, +3, +4, +5. But if I go forward, I'm adding electrons. I'm adding electrons. That would be -5. If I go in the other direction, all right, I'm going across all of D blocks, so that's 10, 11, 12, and argon would be +13. That's wrong also. For gallium and indium, you just have to remember that the charge, okay, this counting to the nearest inert gas doesn't work for gallium and indium. It works for all the other representative metals. All right? It does not work for gallium and indium. For those two, and also tin and lead, you go by the Roman numeral group number. So gallium and indium are +3, +3. Remember, they're losing their valence electrons. So for gallium, they're losing 4s2, 4p1. So if it started out neutral and loses 3 valence electrons, it will have 3 more protons than electrons. The charge will be +3. Right? The same with indium. If indium is 5s2, 5p1. If it loses 5s2 and 5p1, that's 3 electrons it lost. That means it now has 49 protons and only 46 electrons. The charge will be +3. Right? The charge will be +3. All right. We're going to do some more oral drilling, but I'm going to point out one other thing here. I'm going to sit down here for a minute. Oh, man. All right. Now, I'm going to share the screen, and we're going to put back up those lecture notes. What happened to them? Oh, there they are. Okay. Now, we now know what isoelectronic means. Same number of electrons or same electron configuration. Okay? Same number of electrons or same electron configuration. One implies the other. Take a look on the bottom here. All these atoms have 10 electrons. They all have identical electron configurations. All of these atoms in the bottom row are isoelectronic with each other. Not are they isoelectronic only with neon, but they're also like isoelectronic with every other atom in that row because they all have 10 electrons. Remember, each atom is isoelectronic with neon. That means they must be isoelectronic with each other. They must be isoelectronic with each other. Okay? So therefore, if I say, okay, I'm at O minus 2, give me an anion that's isoelectronic. Well, I know anions are negative. Now, I could just go to the nearest non-metal on either side of me. Fluorine minus 1 is isoelectronic with O2 minus, or N3 minus is isoelectronic. How about a cation that's isoelectronic with O2 minus? I go to the nearest inert gas. If I want a cation, I go to the first metal. Sodium plus 1 is isoelectronic with O minus 2, right? How about a second cation that's isoelectronic with O2 minus? Go to the nearest inert gas. Well, I already did sodium. How about Mg2 plus is isoelectronic with O2 minus? I'm gonna put the periodic table back up, and we'll do that again. What I just went over, again, if you have a question or comment, don't hesitate to ask. So let's look at calcium. All right, calcium. Is it a metal or a non-metal? It's a metal, so I know it's positive. Positive how many? Positive 1 at potassium, positive 2 at argon. So calcium's charge is positive 2. Give me another cation that's isoelectronic with calcium plus 2. Well, I'm sitting here at the inert gas. Cations are positive, so all I'm going to do is go to the first metal. Potassium plus 1. Potassium plus 1. Positive because it's a metal. 1 because it's 1 away from argon. Okay? 1 because it's 1 away from argon. Notice gallium plus 3 is not isoelectronic with calcium plus 2. Because gallium plus 3 has all these 3d10 electrons. Right? Don't try to get fancy. Again, my suggestion is when you're asked for another ion that's isoelectronic, just go to the nearest inert gas. If you're asked for an anion that's isoelectronic, then you go to the first non-metal. If you're asked for a cation that's isoelectronic, then you go to the first metal. All right, so if I have beryllium, all right, and I'm asked, all right, what's the charge? Well, it's a metal, so positive, positive 1, positive 2. It's 2 away from helium. What's another cation isoelectronic with beryllium? Well, cations are positive metals. So I'm going to go to the first metal, lithium plus 1. Lithium plus 1 is isoelectronic with Be plus 2. How about an anion that's isoelectronic with Be plus 2? I go to the nearest inert gas, which is helium. Then I go to the first non-metal. All right, non-metals are negative, so hydrogen minus 1 will be isoelectronic with Be plus 2 and Li plus 1 and He 0. Those 4 atoms are all isoelectronic with each other. All right? Let's ask this question here. Let's ask this question. Can 2 atoms with different charges, or sorry, with the same charges, can 2 atoms with the same charges be isoelectronic with each other that are from different elements? Can 2 atoms that have the same charge but from different elements, can they ever be isoelectronic with each other? Two atoms with the same charge but different elements, can they ever be isoelectronic with each other? Nobody has an answer.
No, I don't think so.
No, they cannot. If they have the same charge, let's go back to the periodic table. Okay? One thing we should notice here, all the halogens are -1. Why is that? All right? All the atoms in the same group have the same charge. The halogen, okay, the inert gases are all 0. They don't form cations or anions because they're already at lowest energy. They have completely filled outer shells. The halogens are all -1. Why is that? Well, they're non-metals, so they're negative. And they're all 1 away. Fluorine's 1 away from neon. Fluorine's 1 away from argon. Bromine's 1 away from krypton. So they're all -1. They're all in the same group. They're all -1. Let's look at group 16, right? These guys, as far as the nonmetals here, right, they're all negative because they're nonmetals or metalloids. If you're down here in tellurium or polonium, right? So they're all negative. Oxygen is 1, 2 away from neon. So oxygen's -2. Sulfur is -1, -2, right? Selenium, nonmetal, negative, -1, -2. Tellurium, metalloid, so negative, -1, -2, right? They all have the same charge. Let's look at group 15, okay? Nitrogen, negative, so nonmetal, so negative, -1, -2, -3. Phosphorus, -1, -2, -3. Arsenic, -1, -2, -3. Those all have the same charge in the same group. Let's look over here at the metals. Well, here, we said aluminum is +3, right? Remember, the nearest inner gas is not argon, right? It's 5 away from argon, but it's only 1, 2, 3 away from neon. So aluminum's charge is +3, right? Aluminum, gallium, and indium all have charges of +3. They're in Roman numeral group 3, 3A. All right, the representative metals have charges identical to their Roman numeral group number. Identical to their Roman numeral group number. All right, let's look over here. The alkaline earths. They're all positive because they're all metals. Beryllium is 1, 2 away from helium. Magnesium is 1, 2 away from neon. Calcium is 1, 2 away from argon. They're all +2. The alkaline earths are all +2. All +2. Okay, let's look at the alkaline metals. Remember, hydrogen is not a metal, so it's not an alkaline metal. And remember, hydrogen can be -1 or +1, right? The only representative element for our purposes. So let's look at the other elements of group 1, the alkaline metals. They're all positive because they're all metals. Lithium is +1. It's 1 away from helium. Sodium is +1. It's 1 away from neon. Potassium is +1. It's 1 away from argon. Right? So all of the elements in the same, all the atoms in the same group have the same charge. Have the same charge. Right? Now, let's see. I'm going to stop sharing here and give you a chance. Does anybody want to ask a question? Anybody want to ask a question or make a comment? Everybody's an expert.
I have a question, Raymond.
Go ahead. By all means, proceed.
So when you talk about group 16,
Which group?
16.
16, okay.
So those are non-metals. You only went down to tellurium, but does that include polonium as well, being that it's a metalloid?
Yes, it does include polonium if you want to. I will tell you the reason why I did not do polonium. These are pretty rare elements once you start getting down here. Astatine is really rare. Polonium is relatively rare. Bismuth is not so rare. Bismuth is a metal, by the way. Remember, we draw this line down here. Right, so bismuth is to the left of that line. So bismuth, lead, and thallium are metals. Thallium is very, very poisonous. Right, but yes, we would include polonium as a non-metal. Right, but I kind of stopped because it's pretty rare. Right, it's pretty rare. Okay.
Okay.
Did we answer your question?
Yeah, I did. I just wanted to make sure that when we're
why
looking
I
at it,
stopped
that it was,
at tellurium.
yeah.
Yes, and notice there are some compounds made containing
Where
astatine,
does he
but
get money from?
there's not that many of them. There's not that many. Okay. Any other questions? So again, I'm going to do a few more, and then we'll have you guys do a few. Oh, let's talk about the transition elements for a moment. First off, do they form cations or anions? They form cations because they're metals. All metal elements form cations. All metal elements form cations. All nonmetals and metalloids form anions. Okay, now, why doesn't the octet rule apply to the transition elements? And here's why. We just said the alkaline earths are all +2. They're never anything other than +2. The alkaline metals are always +1, right? You never see lithium +2, right? You never see potassium +2 or +3. They're always +1, right? However, if we focus on iron here, number 26, iron can be +2 or +3, all right? Copper can be +1 or +2. Gold here can be +1 or +3. So in other words, the transition elements can have variable charges. They are cations, positive cations, but you cannot tell the number just by looking at the periodic table. You need additional information, right? You need additional information, okay? There are some that don't have variable charges. For example, scandium is always +3, right? But for our purposes, since this is just an introductory chemistry class, we will consider the transition elements. You cannot predict their charge just by looking at the periodic table. Silver is another one. It's always +1. It's always +1. Right? Manganese here can be +1, +2, +3, +5, +7. Right? So there's no way. If I say, what's the charge on the manganese cation? You don't know. It could be any of those 5 numbers. You need more information. You need more information. But if I say, what's the charge on the sulfur ion? It's always -2. It's never anything other than S-2. Never anything other than S-2. Okay? So let's go to sulfur. And I say, okay, what's its charge? Well, it's a nonmetal, so -1, -2. It's isoelectronic with argon. Isoelectronic with argon. Right? So how many electrons? Actually, we'll get to that in a moment. Let's ask for another anion that's isoelectronic with sulfur, -2. Just go to the first nonmetal, chlorine -1. Chlorine -1. How about a metal that's isoelectronic with sulfur -2? Go back to that nearest inert gas and go to the first metal. Potassium +1 will be isoelectronic with sulfur -2. Right? So again, let's look at all the atoms that are isoelectronic with each other. Argon 0, chlorine -1, sulfur -2, phosphorus -3, silicon -4. They are all isoelectronic with each other. And then on the metal side, potassium +1, calcium +2. They will all be isoelectronic with each other. Okay, they will all be isoelectronic with each other. Okay, do we have any questions there? All right, let's just do a little bit of oral drilling since everybody's an expert here. Let's see. Jasmine's there. Checked in late. Jasmine, put your finger on number 37.
Okay, hold on. I'm kind of driving. Okay, let's see.
You got it?
Yeah,
All right, you're on rubidium, right? Metal or non-metal?
non-metal.
Say again? I didn't hear you.
Oh, that's a metal.
That's a metal. So positive or negative?
Positive.
Positive. Positive how many?
Is it positive? +1.
Positive 1. So it's isoelectronic with which inert gas?
With neon.
How did you go from 37
you-
to 10? What's the
Oh,
nearest
shoot,
inert
my
gas
bad.
to
I'm
rubidium?
trying to zoom in on my phone.
What is it?
Krypton.
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 Right, so it's isoelectronic with krypton. So rubidium +1 is isoelectronic with krypton. Can you give me another cation that's isoelectronic with Rb +1? Another cation. Jasmine, put your
Another
finger on
cation?
krypton. Put your finger on krypton.
Okay.
You have it on krypton.
Yeah.
Go to the first metal. What's the first metal closest to krypton? Rubidium. But that's the one you started with,
Yeah.
right? So go to the next metal. What's the next
Yeah.
metal?
Strontium.
108, please.
Strontium. So strontium's charge is what? Plus how many?
Plus
I
2.
just said.
Plus 2. Now, I'm going to ask you for an anion. It's isoelectronic with rubidium plus 1. So go back to krypton.
Um,
I'm trying too hard. We'll see.
Go back to krypton.
bromine.
Okay.
Now go to, so which elements form
Okay.
anions, metals or nonmetals?
Non-metals.
So what's the first nonmetal that's closest to krypton?
Bromine.
And what's its charge?
-1.
-1. Okay, -1. Let's see here. Joseph, you there?
Yes, sir.
Put your finger on silicon. Metal or non-metal?
That is a
Later, man. Thank you.
metalloid, so it's going to be a non-metal.
So positive or negative?
It's negative.
Negative. Negative how many?
-4.
-4. So it's isoelectronic with which inner gas?
Yeah, except for the
With
one. I think I
argon.
got the one.
Argon. Can you give me another anion isoelectronic with Si-4?
Sure. Phosphorus. It's at -3.
Phosphorus -3. Can you give me a cation that's isoelectronic with Si-4?
Sure. That'd be potassium at +1.
Potassium +1. Potassium +1. Remember, ions must have charges. They must have charges. Right? It's the definition of an ion, an electrically charged atom or group of atoms. All right, good job, Joseph. Let's see. Let's pick on one of the young ladies. Let's pick on one of the young
You
ladies.
got a whole 10 cents.
Who's ever talking there? Could you please mute yourself for a minute? Michaela, are you there?
Yes.
All right, Michaela, put your finger on number 5055. You got it?
Yeah.
Metal or non-metal?
Might as well.
Metal.
Okay, so metal, so positive or negative?
Positive.
Positive. Positive how many?
+1.
+1. Isoelectronic with which inner gas?
Xenon.
Xenon. Can you give me another cation isoelectronic with cesium +1?
Yeah.
Another cation.
Oh, you're up.
Barium.
Would whoever has their microphone on and is talking in the background, can you please mute your microphone?
That's Jamie or Jaime Snetti. You've got your mic open.
Oh, my bad. I'll turn it up now. I'm sorry. I'm at work.
Okay, so let's see, who were we picking on there? Michaela. Michaela, can you give us another cation that's isoelectronic with cesium +1?
Barium.
Charge?
Positive.
Positive how many?
+2.
Barium +2 is correct. Now, can you give us an anion that's isoelectronic with cesium +1?
Iodine.
Charge? Come on, you got to give a charge. You can't just say iodine.
-1.
Iodine -1. Good job. Good job there, Michaela. Okay, let's see. Does anybody want to volunteer?
I'll volunteer.
Who's
Kiana.
Who?
Kiana.
Kiana. Kiana, put your finger on. Number 7.
Okay.
All right, positive or negative?
Negative.
All right, so nitrogen is negative. Negative how many?
-3. -3.
-3. So it's isoelectronic with which inert gas?
Neon.
Neon. Can you give us another anion isoelectronic with nitrogen -3?
Oxygen -2.
Oxygen -2. Can you give us a cation isoelectronic with N-3?
Sodium, -1.
Sodium.
Positive 1.
+1. Sodium +1. All right, good job. Good job, Miss Seaboy. Oh, sorry,
Thank
shouldn't be
you.
saying names, huh? Shouldn't be saying names. All right, let's see here. Now, I'm going to stop here for a moment. Let me bring this back up here. Now, I'm going to send you an assignment on this. It is not due on Wednesday because we haven't covered everything. Actually, we've covered everything but one little section, which we'll do on Wednesday. All right, which we'll do on Wednesday. And again, please try to get your assignments to me. We got to have a quiz here soon, but I don't want to do that to some of you guys haven't turned in a single assignment yet. All right. You got to get these assignments into me. Again, the earlier you can get them in, the better. Again, this one I'm going to send you today. It's going to be called ion formation. Actually, let's bring it up on the screen here. Actually, we'll wait until I stop recording here. Actually, I'm going to stop recording now. So we've had a good introduction to ion formations, at least monoatomic ion formation, right? Meaning one atom ions. Atoms, so ions taken from the periodic table. Right? Remember, ions can also be an electrically charged group of atoms, and we will talk about those in the near future, probably next class. Let's see. So I'm going to stop recording here.